All right, here's the mutually tangent circles problem. You got three circles that are mutually tangent, so each one is tangent to the other. They tell you some things here. One of the things that I use here is that if I have the centers of these circles, um, when I connect them, that the points of tangency are on those connecting lines, right? Because the point of tangency is where you have a tangent line here, and the radius is perpendicular to tangent. So this is perpendicular to tangent, and likewise that is perpendicular to the tangent. So that's just one straight line segment. But that gives me this triangle in here. It looks like a right triangle at the moment, but that's just coincidence. But what I know that the small triangle has radius 8.5, and so this is also 8.5. I know that the middle one is 11.9, and this is 11.9, and then the big one here is 14.7. 14.7. So they ask for the total area bounded by the circle, so the three circles plus the interior stuff, that little wedge inside. And actually, I think the way that's going to be easiest for me to calculate this is essentially calculate the area of the triangle and then calculate the areas of the sectors that are outside. So I'm going to add up three sectors plus one triangle. And in order to do this, I'm going to need to know what these angles are. But I can find those angles because I've got the side lengths of that triangle, right? So I've got this big triangle now here that's got side length 14.7 plus 11.9, so that must be 26.6. This is 14.7 plus 8.5, so that's 20 to 23.2. 23.2, and this other side over here is, what's that, 19, 20.4, 20.4, right? So I'm going to call this one A, and this one B, and this one C. I'm looking at this thing, so this is A, this is B, this is C. One thing when I'm using the law of cosines and the law of sines to find pieces of triangles, I have to be really careful that I don't use the law of sines inappropriately. And the law of sines gets in trouble when you're trying to solve for a big angle. Small angles less than 90 degrees are okay. Law of sines will do just fine. So the thing that I look at here is what's the biggest angle? Solve for that one first. And the biggest angle is always across from the biggest side. So I'm going to use the law of cosines to solve for angle C here. Okay. So side length C, 26.6 squared equals the sum of the square of those two, so 23.2 squared plus, whoops, 20.4 squared minus 2 times 23.2 times 20.4 times the cosine of angle C. By solving for the big angle first, the big angle is the only one that might be bigger than 90 degrees. It might not be, but it's the only one that has that chance. Once I know that, then I know the law of sines will be just fine to get those other two sides. So here we go. Solve for the cosine of C. I'm going to subtract this stuff all over, sorry, add all this stuff to the other side and subtract this. So I've got 23.2 squared still here. I've got the 20.4 squared still here. I'm subtracting this over, so the minus 26.2 squared. This stuff all goes to the other side, so it becomes positive, and then I'm going to divide by all that stuff, except for the cosine of C. So the cosine of C will be that divided by 2 times 23.2 times 20.4. Okay, so I'm going to type this into my calculator, and I get 0.283 and 088, whatever. So this angle C is the cosine inverse of that thing. Now I only wrote down 3 decimal places, but on my calculator I've got it to 10 decimal places, and so I'm just going to say inverse cosine of the answer, so it gets all those decimal places, and it tells me that angle C is 73.555 degrees. Okay. Now, angle C is the biggest angle. It wasn't bigger than 90 degrees. It was only 73. But that tells me that A and B are also smaller than even that. So the law of sines I can use to find them. So here we go. Oh, actually at this point, let me point out that knowing this angle, and so knowing this angle here and these two sides, I can find the area of that triangle by just doing 1/2 of this side times that side times the sine of that angle, right? So where are we now? What's happening? So what I want to do is I want to find the other two angles, because that's going to help me find, if I know all three angles, then I'm going to know what all of these angles on the outside are, and so I can use that to find the area of the sectors. Okay. So here we go. Here we go. To find angle A, I note that the sine of A over 20.4 equals the sine of angle C, but angle C I just calculated as 73.555 divided by 26.6. Okay, solving for A now, it's the inverse sine of 20.4 times the sine of 73.555 all divided by 26.6. And I know I'm going to get the right answer because angle C was the big angle. Angle A is smaller, so it's not bigger than 90 degrees. This will be okay. So I've got the sine inverse of 20.4 times the sine of my previous answer divided by 26.6 for an angle of 47.353 right degrees. So then to get angle B, I'm just going to subtract from 180. So I've got 180 degrees minus the previous answer minus that other one, whatever that was, 73.555. And I get angle B is 59.091. Okay, so here we go. I'm going to redraw the picture here, right? I've got these three circles. I've got this triangle in between them. I can find the area of the triangle area equals this side times that side times the sine of the angle times a half. So it's 1/2, 23.2 times 20.4 times the sine of angle C, which was the 73.555. Okay. So doing that calculation real quick, I get 226.9595. Right. Now I've got to look at those sectors. All right. So let's start off with what do I have for angles here? This is 47.353. That's this angle right here. So the rest of that angle is 360 minus that. So I've got an angle here. I'm looking at angle A here. So on that circle, I've got an angle of 360 minus this 47.353. Now, in order to do the area of a sector, I'm going to use the 1/2 r squared theta, but the theta's got to be in radians. So the first thing I'm going to do is I'm going to take this and convert it to radians. So I'm going to multiply by pi and divide by 180. And then, so that's the angle, and then I'm going to multiply by the radius squared. Well, in that circle on A, what was the radius over there? Where are we? Way back up here. That was the 14.7. So I'm going to take that 14.7 and square it. So that's going to be this Pac-Man area around angle A is going to equal that amount, right? Whatever that is. Likewise, I'm going to do the same thing around angle B. So I got angle B here with a Pac-Man around it here. That's B. So angle B was the 59.091. So again, I'm going to subtract, that's this angle. So subtract it from 360 degrees, 59.091. Convert it to radians. Oh, did I forget to multiply by a half here? Because it's 1/2 r squared theta, isn't it? So let's divide by 2. And likewise here, we now take the radius of the circle over here, and I've forgotten what it is now. What was the radius of that one? 11.9 was that circle over there. So I've got the 11.9 squared over 2, whatever that area equals. And lastly, I've got angle C with its Pac-Man around it. That angle was the 73, so 360 minus 73.555. That's in degrees. Convert it to radians. Multiply by the radius squared over 2, and the radius of that bottom circle is, what is it, 8.5. There we go. Over 2. And the total area is going to be this Pac-Man plus that Pac-Man plus that Pac-Man plus the area of the triangle that we just calculated here. So again, I haven't finished this problem, but do this calculation, this calculation, this calculation, and add up all of these 4. 1, 2, 3, 4. And that should be the total area around, inside the whole thing. Not a simple problem, but all the pieces are there from what we've learned. So there you go.